Right now, as you watch this, a chunk of ancient ice older than our entire solar system is drifting away from us, heading back into the darkness between the stars. It spent somewhere between 10 and 12 billion years silently crossing the galaxy before it briefly wandered close enough for us to study it. Our solar system, for reference, is only 4.6 billion years old. That means the frozen material inside this object was already drifting through space billions of years before our sun even ignited. And here is the part that makes this story genuinely unusual. Two of the most powerful observatories ever built, the James Webb Space Telescope and the brand new Vera Rubin Observatory, both ended up studying this exact same object. One of them did it completely on purpose. The other did it entirely by accident, capturing high-resolution images of this interstellar visitor 10 full days before anyone on Earth even knew it existed. And when Webb finally broke down the light coming off this ancient traveler, the chemical fingerprint it found did not match anything ever recorded in a comet from our own solar system. Stay with me, because the real science behind this object is far stranger than anything the speculation could offer. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to where this story actually begins. On July 1st, 2025, a robotic survey system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, flagged something moving through our solar system from a facility in Rio Hurtado, Chile. The object received the technical designation C/2025N1. At first, it looked like one more faint smudge crossing the sky. But within days, astronomers confirmed something that immediately changed the stakes. This object was not bound to our sun. It was on a hyperbolic trajectory, meaning it had come from outside our solar system entirely, and it was never coming back. It was given the official name 3I/Atlas, the third interstellar object ever confirmed in human history. The first had been Oumuamua, spotted in October 2017 by a survey telescope in Hawaii. Oumuamua was strange because of its elongated shape and a small, unexplained acceleration as it left the solar system, which most astronomers concluded was likely caused by natural outgassing, though the object was already too faint and too distant by the time telescopes caught up to directly confirm that. The second interstellar visitor was Borisov, discovered in August 2019 by an amateur astronomer in Crimea. Borisov behaved much more like a conventional comet, complete with a visible tail and coma, which made it easier to study and compare to comets born inside our own solar system. Now, 3I/Atlas had arrived, and it was, in several measurable ways, the most extreme of the three. Its orbital eccentricity was approximately 6.14, an extraordinarily high number. For context, an eccentricity of exactly 1 marks the boundary between an orbit that loops back and one that escapes forever. At 6.14, there is no ambiguity. This object was moving at roughly 137,000 miles per hour, about 221,000 kilometers per hour, on a wide open trajectory that was never gravitationally captured by our sun at any point. It arrived from somewhere else in the galaxy, passed through briefly, and it is now leaving permanently. But before we get to what Webb found when it pulled this object's chemistry apart molecule by molecule, we need to talk about what happened at the Vera Rubin Observatory, because that is where this story takes a turn that nobody planned. The Vera Rubin Observatory sits on a mountain called Cerro Pachon in Chile's Atacama region, a site chosen specifically for its dry air and dark skies. At its heart is the Simony Survey Telescope with its 8.4-meter primary mirror and the LSST camera, the largest digital camera ever constructed, capable of capturing 3,200 megapixels in a single exposure. In the summer of 2025, Rubin had not even officially begun its real mission yet. It was still in a testing period called science validation, essentially a dress rehearsal where engineers check every system, the optics, the camera, the data pipelines, before the full 10-year sky survey starts. During this phase, the telescope was being pointed at various patches of sky simply to calibrate image quality and system reliability. It was not hunting for interstellar objects. It was not hunting for anything specific at all. And yet, on June 21st, 2025, 10 full days before Atlas announced the discovery of 3I/Atlas, Rubin's camera happened to be pointed at the exact patch of sky where this interstellar visitor was quietly passing through. Nobody at Rubin knew it was there. The telescope continued photographing the object through July 20th, collecting nearly 100 exposures in total. Researchers only realized what they had after the official Atlas announcement, when they went back through their archived commissioning data specifically to check whether the object might have shown up earlier by coincidence. And it had, sitting quietly in the background of ordinary calibration images 10 days before the rest of the world even knew to look. A team led by astronomer Colin Orion Chandler, along with more than 300 collaborating scientists, eventually used 49 of those images in a full scientific study published in the Astrophysical Journal Letters. They measured the object's position across 6 different filter bands with a typical precision of about 70 milliarc seconds, an extraordinarily tiny angle when you consider how faint and how far away 3I/Atlas was at that point. For comparison, Rubin's precision on fixed background stars is even sharper, closer to 3 milliarc seconds. The slightly coarser measurement on 3I/Atlas simply reflects the challenge of tracking something that is actually moving relative to the background sky. Now stop and sit with that for a second. The most powerful survey camera ever built, not even officially operational yet, accidentally photographed an interstellar object before any human being knew it existed. That is not a failure of detection. That is a preview of what this observatory is going to be capable of when it is running every single night for the next decade. But here's the part of this that stops being abstract and starts being personal. Rubin's images revealed something unexpected about the object's tail. Under normal circumstances, a comet's dust tail points away from the sun because sunlight physically pushes dust particles backward. But 3I/Atlas had a dust component that appeared to point toward the sun instead of away from it. Researchers explain this using a process called anisotropic dust emission, meaning the dust was not being released evenly from the surface. It can create unusual tail geometries depending on the viewing angle. It is a known effect, documented in at least one other distant comet. Strange but explainable. And that distinction matters. Because the chemical composition that Webb later uncovered tells us something far more profound about where this object came from, and by extension, about the raw ingredients that exist in planetary systems across our galaxy. The organic molecules, the water, the carbon compounds locked inside this ancient ice are the same basic categories of chemistry that played a role in how life eventually emerged on Earth. We do not yet know exactly what 3I/Atlas's specific chemical ratios mean for the broader question of how common or uncommon those conditions are elsewhere. But the fact that we now have a direct physical sample from another region of the galaxy, from a completely different era of cosmic history, and that we can measure its chemistry in detail, that is itself a shift in what questions we are even able to ask. Now let's talk about what happened when things got complicated. On August 6th, 2025, the James Webb Space Telescope turned its near-infrared spectrograph, an instrument called NIR-SPEC, directly at 3I/Atlas. This was Webb's first real look at the object, and it followed observations already made by the Hubble Space Telescope and NASA's SphereX mission. Webb's role was different from Rubin's. Rubin captured images, essentially photographs showing shape, brightness, and movement. Webb went further, using spectroscopy to break down the light coming from the comet into its chemical components, almost like reading a molecular fingerprint. And almost immediately, Webb found something that did not fit the expected pattern. Inside the comet's coma, scientists detected carbon dioxide, water, water ice, carbon monoxide, and a sulfur compound called carbonyl sulfide. All of these are fairly standard comet ingredients on their own. But the ratio of carbon dioxide to water was among the highest ever recorded in any comet, solar system, or interstellar. The CO2 to water mixing ratio came in at roughly 7.6, significantly above the trend line for long period and Jupiter family comets. That ratio matters because it tells astronomers something specific about the temperature and radiation conditions in the environment where this object originally formed. A comet born in a system flooded with sunlight and warmth produces a very different chemical balance than one born in a cold, radiation-heavy region far from its parent star. This first set of results was published in the Astrophysical Journal Letters, led by Martin Cordner at NASA's Goddard Space Flight Center. Then in December 2025, Webb looked again. 3I/Atlas had just passed its closest approach to the Sun on October 29, 2025, a moment scientists call perihelion, and its ancient ice was rapidly converting into gas, producing a brighter, more active coma that was ideal for detailed chemical analysis. Webb captured this second round of observations as the comet was moving away from the Sun, freshly warmed, its deep layers of ice now exposed and outgassing for what may have been the first time in billions of years. If you are the kind of person who wants space stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. And this is where the findings became extraordinary. Using NIR spec, the research team measured specific ratios of carbon isotopes and deuterium, sometimes called heavy hydrogen, locked inside the comet's ice. Deuterium is a heavier version of a normal hydrogen atom, and the ratio of regular hydrogen to deuterium in ice acts almost like a chemical clock. That ratio changes very slowly and predictably based on the temperature and radiation conditions present when the ice first formed, and the deuterium levels in 3I/Atlas were staggering. The water in this comet contained more than 10 times the deuterium found in any known solar system comet, more than an order of magnitude higher. Its carbon isotope ratios, specifically the ratio of carbon-12 to carbon-13, also exceeded typical values found in the solar system, in nearby interstellar clouds, and even in protoplanetary disks. Think about what that means. This is not a subtle difference. This is a chemical signature that sits completely outside the range of anything formed in our cosmic neighborhood. Working backward from that isotopic data, the research team was able to estimate not just how old this ice is, but roughly what kind of environment produced it. The extreme deuterium enrichment points to formation temperatures below 30 Kelvin, which is roughly minus 243 degrees Celsius, in a relatively metal-poor environment early in the history of the galaxy. When interpreted against models of what scientists call galactic chemical evolution, the carbon isotope ratios imply that 3I/Atlas accreted its material roughly 10 to 12 billion years ago, following an early period of intense star formation, sometimes called cosmic noon. For perspective, the universe itself is estimated to be about 13.8 billion years old. This comet may have formed when the Milky Way was still in its youth, long before our own corner of the galaxy had even begun assembling the cloud of gas and dust that would eventually become our sun and planets. These findings were formally published in the peer-reviewed journal Nature on June 22, 2026, in a paper titled Isotopic Evidence for a Cold and Distant Origin of 3I/Atlas, led by Martin Cordner along with co-authors including Nathan Roth, Marco Micheli, Stephanie Milam, and Cyrielle Opetom. A separate complementary study by Opetom, using the European Southern Observatory's Very Large Telescope, analyzed the comet's carbon and nitrogen isotopes in the form of cyanide, adding another independent line of evidence pointing to the same ancient, distant origin. Now stop and sit with that for a second. This is a frozen relic, a physical fragment of an ancient planetary system that formed when the galaxy was still young, preserved essentially unchanged for the majority of the universe's entire existence, and it just happened to drift close enough to our sun for us to study it in chemical detail before it disappears again forever. Now let's talk about what is happening right now. 3I/Atlas has already passed its closest point to the sun and to Earth. At its nearest, it came within about 170 million miles of our planet, roughly 270 million kilometers, posing zero threat at any point. It is now moving back out of the solar system, heading into deep interstellar space again, quietly and permanently. Scientists coordinated observations across an extraordinary lineup of instruments to study it during its brief visit. Hubble helped estimate the size of the solid nucleus, placing it somewhere between about 440 meters and 5.6 kilometers wide, a wide range that reflects the genuine difficulty of measuring a small, distant, actively outgassing object when its bright surrounding coma hides the true edges of the solid core underneath. NASA's SPHEREX mission detected infrared signatures of dust, water, organic molecules, and carbon dioxide. NASA's TESS mission, normally used for hunting planets around other stars, was redirected for a special observation run to study the comet's activity and rotation. Even ESA's JUICE spacecraft, currently on its way to study Jupiter's moons, managed to capture images of 3I/Atlas in November 2025 from its own position in the solar system. In total, this makes 3I/Atlas one of the most thoroughly observed interstellar objects in history, and the Vera Rubin Observatory itself has now officially begun its real mission. The Legacy Survey of Space and Time, or LSST, started on June 30th, 2026. For the next 10 years, Rubin will photograph the entire southern sky every few nights, generating more data than all prior observatories combined. The fact that it accidentally photographed an interstellar comet before it was even officially operational, while still running calibration tests, is a genuine preview of what this telescope is going to deliver when it is scanning the sky systematically, night after night, for an entire decade. Scientists expect more interstellar objects to be found over the coming years. And when they are, there is a very real chance Rubin will be one of the first instruments on Earth to spot them, simply because, unlike almost every telescope before it, it genuinely never stops watching. Here's what I want you to take away from all of this. Two observatories designed with completely different strengths ended up studying the same ancient traveler. Rubin is built for speed and coverage, scanning enormous sections of sky constantly, which is exactly why it caught 3 I/Atlas entirely by accident. Webb is built for depth, for incredibly precise chemical analysis of a single target at a time, which is exactly how it traced this object's origins back more than 10 billion years. One telescope found the object, the other figured out what it was, where it came from, and roughly when it was born. Neither discovery would mean nearly as much without the other. And together they revealed something that deserves to land harder than it usually does. This was a message in a bottle. Not sent deliberately, not aimed at us, not encoded with meaning. Just a frozen chunk of ordinary ice and dust assembled in a cold cloud of gas around a young star in a young galaxy, ejected into the void billions of years ago, drifting alone through the emptiness between stars for longer than our sun has existed. And then, by pure chance, it wandered close enough to a small blue planet for a handful of telescopes, some on a mountaintop in Chile, one orbiting 1.5 million kilometers from Earth, to photograph it, analyze its chemistry, and calculate roughly how old it actually is before it disappeared again for good, likely never to be seen by human eyes or instruments again. One ancient visitor, one brief pass, one chance to look. If you want to keep seeing real, fact-checked breakdowns like this one every time something genuinely new happens in space, subscribe now and turn on notifications. Stories like this are only going to become more common as Rubin Observatory settles into its full 10-year survey and Webb keeps doing what it was built to do. Drop a comment and tell me which detail surprised you most. The accidental discovery 10 days before anyone knew to look, the chemical signature that sits completely outside anything in our solar system, the fact that this object may be nearly as old as the universe itself, or the sheer number of telescopes and spacecraft that turned to study it before it left us for good. And share this with someone who needs to hear it, because this story deserves more than the silence it is getting.